So I know we got a little bit further than this yesterday, but I'm going to pick up here and then we'll move along. Because where we stopped yesterday was talking about set builder notation. And set builder notation is really helpful when trying to describe large sets of numbers or unique groups. One of those two. Because as we saw yesterday when we talked about, so when we talk about, say, all of the odd whole numbers, well, we can't list them out. It would be hard to list them out. And that's what this here gives us, is an easier way to write it. Now, for the most part, set builder notation will be used here for Chapter 1.1, Chapter 1 review, Chapter 1 test. And then we won't really talk about it much at all. Because for the most part, unless you're doing proofs of some type or kind of mathematical research where you're talking about specific numbers or groups of numbers, not so much statistical research, but maybe, then you'll use this. But most of the time you won't really talk about set builder notation, because we could really just say it's all the odd whole numbers, or in the study we're talking about the odd number of patients, the ones that came through the door are going to be considered this. And we won't really need to, because if you're talking about every odd numbered patient that came through the door is going to be falling under whatever notation. We don't actually have to consider it as whole numbers. We don't have to set that quantifier, because we can't have a fraction of a person unless for some reason you decide to be morbid. And I don't think that's considered ethically right anymore. So we cut that out, and you can't have negative people. You can have negative emotions, but you can't have -1 people come through the door. It just doesn't work that way. So there are some, when we talk about realistic standards, that kind of fall in, that we know that these just aren't realistic. They throw them out. But for us, we're just going to be talking about the pure numbers. Now, I believe we got to this here. We got through these here yesterday, and we stopped here. Yes? Okay. So that's where we'll pick up today. Oh, that's right, because we did the ones before y'all said we were good here and moved on. So we'll just look at this here, because we talked about this one. -6, -2. Circle, hole, everything in the middle. So let's look at number 5. So for all real values x, such that x is less than or equal to 0, or x is greater than or equal to 10. Well, our 2 points are 0 and 10. And we know 0 has to go on the left, 10 is on the right, because, well, 0 is smaller than 10. Now we will have 2 circles at both of these here. Will both be open, both be closed? Both will be closed, because they are both equal. So here x is less than 0. So we shade to the left or to the right? X is greater than 10, we shade to the... That's it. And this is where we ended, where we were actually going to start talking about set builder notation. Now, whenever we talk about set builder notation, this is where we're going to really start with our brace x. Now, before we put the bar down, we need to see what types of numbers we're talking about. Well, this here says the set of all integers. Now, most likely, I think what the book is going to say is going to tell us x is an integer. It's literally going to write it out. I don't like that. Not because it's technically wrong. It's not wrong. That is right. But the mathematician in me doesn't like it, because I don't want to have to write out x is an integer. Way too many words. What we can use is this little e. So it's not an actual e, it looks like an e. It looks like a little trident, or the top part of a trident. What that represents is an element. What we're saying is x is an element, or x is an, what do we want it to be? Integer. So what this is saying is we can read it as one of two ways. We're either saying x is an integer or x is an element of the integers. So in the group of integers, positive and negative, we're saying x is one of them. X is one of the numbers in the group that we call integers. Now we can do the such that. Now we can drop the bar. Okay. So we classified the type of numbers. X is an integer. Such that what? Greater than 5. So x is greater than 5. Close it up. We made that sentence a lot nicer. I think it looks nicer. It's a lot more compact and a little bit understand. As long as you understand what we're looking at, the symbols, x is an element of the integer such that x is greater than 5. X is an integer and is greater than 5. Any questions on this here? All right, let's look at the next one. Well, I'm going to draw this out. You don't have to. Now, the first one, we have -1. I have a circle, and it's everything to the left of it, yes? Because that is the interval notation for telling me we have all the numbers less than -1. Now, the other statement is that I have all the numbers greater than -1. So really it's saying what? It's all real numbers except for -1. So let's start step builder. Brace x. What kind of numbers are we dealing with? Real. Because when we talk about intervals or inequalities, if it just gives us inequalities or an interval notation, we're talking about all real numbers. We're talking about all of them. So that means I can just put the bar. Because the only way I'm not going to put, the only reason I would put something in there is if we're talking about something that's not the real numbers. But we're saying for all real numbers, all of them, what? X is greater than or x is -1. So we have all of them. This here is another way we can write it. In mathematics, that V is OR. When we talk about proofs and proof-based doing proofs, instead of writing OR every time, they use V's. What do you think if we flip the V upside down? We made it look like a tent. So it wouldn't be OR and. And and OR are the two main ones that they have. So if it's flipped over, it is and. If it's flipped up, it is OR. Above and beyond. Now, there is a third way to write this. Because this here is saying the set of all real numbers x, yes? We have all of them. Our interval notation told us we have everything except what? What is the one value we can't have? So what? X cannot be what? -1. That is the exact same thing. And it's really dealing with the fact that we started off with saying X is all real numbers. For all real numbers X, such that, well, X is not -1. That's what that says. That's what that says. They are the exact same thing. If this was somehow included in a research paper, mathematical research paper, they will pick this. You might think I'm being silly when I say mathematicians are lazy. They are lazy. Any proof that's already been proven or shown doesn't have to be reproven. If you're doing a research paper and you require the proof, you don't re-show it. You just say reference such and such. Heard of one guy who did a research paper and went on and did the proofs for everything. It was over 200 pages, submitted it. They returned it with edits that had cut it down to 70. Because like, yeah, this proof here, no, you just write reference this guy's name or paper, you're done. You reference this paper, you reference, and they just hacked it up. So once we prove something, we don't ever reprove it again. If y'all remember back to geometry, for those of you who had me in there, because a lot of the stuff we did with right angles, triangle congruency, we didn't use it or reference it until we had proven it. Once we proved it, we said, yes, this is true. Because once we prove something, we don't have to prove it again. All right, let's look at these here. Let's look at number 6. Because we'll look at most all these here because this here is something you're not as used to. Well, we need to start out with X. So what kind of numbers are we dealing with? All real numbers. So we just have, for all real numbers X, such that, what?
Is less than or equal to -1.
Mm-hmm. Or?
X.
Yep, greater than 1. Now, we can't use the nice little trick we had on last one because, well, there's a lot of numbers between -1 and 1. That space is huge. The amount of space between -1 and 1 is massive. The space between 0 and 1 is infinite also, because we can fit almost every single number in 0 to 1. Because we can put it as 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5. Well, there's an infinite number of those, yes? And we could do it with any other type, because we could change it to 1 over 2 times 1, 1 over 2 times 2, 1 over 2 times, I mean, there's different ways we can create those decimals and keep expanding out the denominator and make it big. So we can't use that kind of trick where X is not equal to, because we have a huge gap between them. Okay, let's look at the next one. This one you'll probably like out of most of them, the set of all integers except -4. So we'll start off the same. Brace X. But what do we need next? Almost. Easy with our 2 bars. Our symbol for integers, because we would use the straight bar if it was real numbers. Since it's integers, we have this. X not equals -4. That's it. Questions on this here? Throw that on the ground. Be ready for the next ones. So this here, I moved it because last year's I didn't like where it was placed. It was placed at the beginning when we were talking about sets and subsets and interval notation and set builder, and some of this was requiring set builder. I didn't like where it was placed last year and the years before, and I kept saying, I'm going to fix it. And then at about this, when this showed up during the lesson at the other end, I would remember, I need to fix it. And I've been saying that, I think I said that for 2 years in a row, so third time's the charm. But what we'll be looking at these here is going back between set and set builder. That whole hyperbola or tangent is just to say that. And it's going to depend on what we have. The whole numbers 50 through 54. Can we list those out in a reasonable amount of time? So what would they be? 50? Are we done? Okay, well that wasn't bad. 50, 51, 52, 53. I could say that is about as fast as I can write it, isn't it? So that there we can write as a set because whole numbers means we're not talking about decimals or fractions. We don't have any irrational numbers than non-repeating, non-terminating decimals. We don't have any of that. We just have these 5 numbers. So we can write it as a set. We don't need set builder notation because it's not something that's arduous to write. I'll go on and write it in set builder. You don't have to do this because it would be the set. So for all real numbers, x in the whole numbers such that 50 is less than or equal to x is less than or equal to, that's not any easier because we put about the same amount of work, and for y'all trying to think through that, it's going to be the same amount of work as just writing 50, 51, 52, 53, 54. It doesn't improve anything. And that's really what it's going to come down with all these here. What's going to be easier? What's easier to write? Either write it as a set or using set builder notation. Okay. How about this one here? The real numbers 0 through 4. So can we do that? So 0, then what? Well, we'd have 0, then we'd have 0.000000009. I mean, we have all those decimals, all those fractions, all those irrational numbers. There's so many numbers between 0 and 1, let alone 0 and 4. This is here is where we would use set builder notation because it's not really easy to write all those. And because it is all real numbers, we can just do brace x such that what is less than, because it's 0 through 4. So stuff like this on the test, especially if this is what I put down as the correct answer and you get it marked wrong because you put equals on both sides, if you can essentially persuade me to know this by what you were thinking and how you were thinking of the terminology and use of the words, I may or may give you it back. Okay? The integers, negative 100 through 100. So this here doesn't include the decimals because we're talking about integers. But how many numbers would we have? 200 or it's either 201, I think. Yeah, or 199. So, but that's still a ton of numbers to write. I'm not going to write that many numbers. So we'll use set builder. So we don't have all real numbers. We have the integers. So we'll have e z such that under it is x is less than so as I was referencing earlier, we can leave it as this here, but the textbook considers through to include both of them. Those through. So I'm not going to be as big of a nitpick on that because I don't like their use of the word through, because I think it is going from, actually, yeah, going from one to the other. So it would be that on the other one, but I like better terminology. So, but it is what it is. Questions on this here? So technically, this here should be that as well, because it's going to 1, 0 is less than or equal to x is less than or equal to 4. I'm not worried about prime numbers. Because I feel like they're going to be cheap anyways. And say x is a whole number such that x is prime. No. Let's see. Yeah, so they didn't do whole numbers. They said x bar, x such that x is prime and x is a whole number. Yeah, like that. The reason we can't use any other notation or any way to describe it is because we technically haven't described or found all the prime numbers. There's still more, and there's not a unique way to actually identify what they are. The Riemann's, if I remember correctly, so don't quote me on this, I think it's the Riemann's hypothesis is one of the $1 million prize math proofs. So if you can prove it, you'll get an award and $1 million for solving it. It helps kind of define any and all ways that we can actually find the next primes. So to be able to find all of them. But that's it. That's all we're doing for today. Because the others are essentially the same thing for all real numbers x such that x is a natural number, x is a rational number, x is a real number. So this is your assignment on page 7, problems 5 through 14, 17 through 24, 26, and 27. And that is it.